Hello, and welcome to this Luna Innovations webinar. My name is Matthew, and I will be your Global Spec moderator, and I want to review a few housekeeping items with you before we begin. Please take a moment to familiarize yourself with the operation of the user interface for today's webinar. The large window with the heading Presentation in the upper left is the primary window for today. Just to the right of the main presentation window is the Speaker Bio window, with background information on today's presenters. And just below that is the Q&A window. At any time during the presentation, you can enter a question into the box in the lower section of the window and click Submit. Your question will be placed in the queue to address when we get to the Q&A session. At the bottom of your screen, you will see additional buttons to enhance your webinar experience. To see what a particular button does, just place your mouse pointer over it and a tooltip will appear with a description of the button's function. And now, I would like to introduce today's presenters. With us today, we have Dr. Earl Dooling, the Director of Business Development, coming to us from Luna Innovations. And we also have Josh Gibson, the Gauging Industry Technology Manager, coming to us from Quad Plus. To read more about our presenters, please look at the Speaker Bio window right next to the main presentation window. And now, I would like to bring in Dr. Earl Dooling, who will be introducing Luna and himself, and then we'll hear from Josh, who will introduce Quad Plus. We'll hear a bit about that, and then we'll get into the presentations. So, Dr. Dooling, please go ahead.
Great, thank you, Matthew. Today we're going to talk about steel pipe coatings. Infrastructure is made with steel pipes, and those need to be coated in order to prevent corrosion and degradation of the pipeline over its lifetime. We'd really like to present how we can use Terahertz products to actually measure the thickness of those coatings in production, saving time and money for the manufacturer. But first, just a word about myself. Involved in the Terahertz field since its inception. I was there for some of the seminal work at the beginning of Terahertz production, and I've been involved with the products that you'll hear about today since 2006 that are manufactured by Luna Innovations. Luna Innovations is a global company, and in addition to the Terahertz products, we manufacture fiber optic as well as distributed temperature, strain, and acoustic sensors, and we have about 350 employees, a little bit more than that worldwide. Josh, would you like to introduce yourself?
Sure. Thanks, Earl. I'm Josh Gibson. I'm the Gauging Industry Technology Manager for Quad Plus. Quad Plus is a large electrical systems integrator. I've been with Quad Plus for going on about 10 years now. We got into gauging because we wanted to fill the gaps that the current gauging suppliers weren't doing and advance some of the technology that's involved in the gauging process. So, Earl, you want to get us started?
Sure. Just as a quick introduction to Terahertz in general, we call it Terahertz. That's referring to the frequency of the that we're generating, generally between 1 and 3 terahertz in that range. That portion of the spectrum is in between the millimeter wave or the microwave and the far infrared. There's some very nice properties about this area of the spectrum. One, it's incredibly safe because it's down in that thermal portion of the spectrum. Your body puts out more terahertz than our sensors do. So there's absolutely no difficulty with having humans around these energy sources. The interaction with material that Terahertz has, and this is one of the reasons why we really like to use it, is that it can penetrate through most non-conductive materials. You see a list on the left, certainly the air, but plastic, gasoline, paper, fatty tissue, most paints, glass fiber composites. Terahertz can penetrate right through those, and so we can have a chance to measure that both the structure the internal structure and the thickness. It's strongly absorbed by water, so we want to stay away from wet things. A little bit is okay, but too much will just absorb. As water is a polar liquid. And for that reason, we really can't look much into the body because we're mostly water. It's reflected strongly by metal. So of course, that's going to figure into the measurement of these pipe coatings. And carbon fiber is also conductive in one direction, and so you can't get through that either. The product has evolved from the laboratory all the way tools to some early manufacturing work with NASA on the space shuttle to our more compact versions, and now the T-Ray 5000, which we've been building since 2012, and we're currently bringing out the latest generation of that product called the 5600, which I'll show you a picture of later. But over that evolution, we've made the systems more compact, more robust, more manufacturable, and phenomenally less expensive by almost a factor of 10. The sensor itself consists of a control unit, which has a short pulse laser and high-speed electronics in it, as well as a computer. And that the signals are transported out to the sensor over an umbilical, and then that industrial sensor that you see here is a bus thing that can that will look at the product, whether that's scanning or robot mounted or a fixed location. It has all its UL, CE, and FCC certifications. It's a robust packaging. The umbilical can be up to 45 meters long. So typically the control unit is put in a cabinet somewhere and the sensor head is out on the production line. Oh, sorry, there we go. So now this is a picture of the new 5600. It's rated from 0 to 50 degrees C, which gives us a nice range for industrial environments. It can plug into pretty much any line power, and it is rated as a Class 3R laser product. But that means that there's no eye protection required if the umbilical happens to be disconnected when you start the system. Still perfectly eye safe. Comparing that to this gauge to other gauging technologies, one of the key features is that it's harmless. Many coating thickness measurements are made either with some sort of a nuclear gauge or with X-ray gauges, and those are obviously can be damaging to humans. Are less easy to use. In our case, we're perfectly safe and don't require any kind of a radiation safety officer or special controls around the operating conditions. It penetrates opaque materials as well as transparent materials. It's a non-contact measurement, unlike ultrasound that has to have a couplant in order to make the measurement. We can look at multiple layers, and even more systems can look at the density of a material as well as its thickness independently. It's very high speed and high precision, and we'll get into some of those details in a bit. We make a variety of sensors for different uses. The one in the lower left is actually Class 1 Division 1 certified, so it can go into explosive environments. The ones across the top, various industrial sensors, and the smaller one at the lower right is meant for robot mounting and has actually 2 ports on it, so that sometimes we can stare at the same product from 2 different directions. The kind of data that we can certainly scan it over a product and get imaging, as shown in the upper left. Just below that is a cross-sectional image, so this is time in the vertical direction and space in the horizontal, where you can actually, a lot like you would get with an ultrasound image. We can certainly do spectroscopy because we're a broadband source. We're putting out a very short pulse, which has a broad bandwidth. And in an industrial application where we typically scan across a product, you'll get some sort of a profile, a thickness profile, and you'll see some examples of that from Josh later on. Then we also make some handheld tools for non-destructive testing, the subject for today. The way that the system works is that the transmitter, shown here in the upper left, emits a short pulse. That pulse then bounces off whatever we're looking at. We'll get a reflection from each interface, and by measuring the time delay between those two pulses, if we know the speed of light in the material, we can tell you exactly how thick that layer is. Just to show, in the case of coating, and in contrast to this condition where I was looking at a freestanding, say, sheet of plastic or coating or object, you're going to get a pulse which are opposite in sign. That's because you're going either into the product or out of the product. But in the case of a coating on a metal substrate, you're going to get two positive reflections. You're going to get a positive reflection from the top surface and underneath metal substrate. So what does the raw pulse look like? Here's an example. As you can see, it goes both positive and negative. That means we're actually looking at the light wave itself, not only its amplitude, but actually its phase as a function of time. So we get a lot more information by doing that, but also you can see that we're effectively hitting an antenna and it's ringing one time off. Now, there's still some little wiggles afterwards, so we like to take this and mathematically transform that, do a deconvolution. I'll say that in this particular example, our waveform duration, meaning the time from the left side to the right, is 160 picoseconds. That corresponds to about 1 inch in space, in reflection. And we can scan over that range 1,000 times a second. So we can make measurements at a kilohertz with this system. By mathematically transforming that pulse, we can turn it into a more ideal representation of itself. That gives us a very nice tool to use as to reflect off of some material. And there's some art in setting the exact shape of this pulse due to the type of filter that we use in the deconvolution process, but that's a detail really. That's part of the initial setup. In this case, I'm reflecting off of a plastic sheet, and you can see the reflection from the first surface of the top surface of the plastic, and a reflection from the backside of the plastic after the pulse is transmitted through it. And so I'm getting a reflection back from both sides. We have a very simple point and click interface that allows you to which peaks you want to find in the pulse train, and you can see and then once those are fit with a green overlay line here, then that allows us very accurately to measure the time location of those pulses to within a femtosecond, which is 10 to the minus 15 seconds. It's a very short period of time. And then by amplitudes, one of the real strengths of our software is that you have this little script interface where you can take those times and amplitudes, process them in the way that you want to, and then come with an output, which means you're not reconfiguring hardware, you're not changing the sensor itself in order to get one measurement or another. You just have to change the equations that you're putting inside here. You can do filtering, you can do set limit, do averaging or whatever you'd like in this box. And then the output, in the case of this case, I'm just measuring this TH00 or the thickness. It's a difference in time multiplied by the speed of light. And I get out a thickness over here of 3.18 millimeters. If we look at that on just a strip chart, we can see I'm getting 3.18 millimeters. Actually, the 2 sigma of the measurements on that measurement screen are just less than a micron. So we're very precise measurement, and even at this high speed of a kilohertz. If we look at that over time and try to see what our stability is, because of course, if your equipment isn't stable, you're not going to get a stable measurement. In this case, we did a little averaging to narrow down so we would see any kind of drift. And we're getting, this was over, I think, 15,000 or, is multiple days of measurement. And we're getting a very tight, certainly much less than a micron kind of distribution. So that's a quick introduction to what we do with Terahertz. And at this point, I want to hand it over to Josh to actually talk about the application of using this for steel pipe coatings.
Thanks, Earl. So yeah, as Earl described, I mean, basically they make the sensor that can make the measurement, and then Quad Plus takes that sensor and integrates it into a system that can be used in an industrial environment and actually give the information to operations itself. So this is kind of showing here, a multi-layer coated pipe, steel pipe on the bottom with multiple different coatings, and you can kind of see in the lower right what the actual waveform would look like. So depending on how many coatings there are, you're always going to get pulses back of N plus 1. So if there's one layer, you're going to get 2 pulses. If there's 3 layers, you're going to get 4 pulses. And with the refractive index difference between those products, that allows us to measure individual layer thicknesses. So we can report back the thickness of all 3 layers simultaneously on a single coated pipe. Just for another example, here's a 2-layer coating. And even with really thin layers, you can still see those coating thicknesses that are being reflected back from the sensor itself. So another concern is coverage and over coverage. A lot of pipe manufacturers will over cover so they don't have to do rework. And weld seams are one of those areas. They'll do over coverage on those for a kind of a safety factor. But being able to do live measurements in closed loop control, we can give you accurate measurements over those areas. And you can do a reduction in material used and potential large cost savings in those reductions of material used. So how do we implement this into an actual industrial environment in a pipe coating application? So there's a few things that you have to take into effect. One, the pipe is moving. So the pipe is traversing out of the pipe coating station. The pipe is also rotating. And they can also run many different pipe diameters as well. So the deployment that we typically use is we use a robot. So we basically put the sensor in an environmental enclosure at the end of an end effector on the robot. And then we gather the information from the line of what the pipe diameter is, and we can automatically adjust for different pipe diameters. So as the pipe is traversing, the robot will bring the sensor over to the pipe itself and start taking measurements. So we can also do automatic stabilization for optimal focus, for pipe distance, lateral resolution, and signal compensation, because this pipe, they're not always that stable. This pipe can move, it can have wobble. So we can account for those in several different ways. One of the ways is we use a large time window of terahertz. So as Earl was describing earlier, on a 160 picosecond unit, we will typically use a 700 picosecond unit to get a wider time window to allow for a little bit of that instability in the pipe. And that's one of the nice things about terahertz and time domain is we can account for that in the measurement. As it moves in the time measurement, the time stays the same. So it's kind of a nice deployment of it. But we also use, to measure where the pipe is, we also have 3 lasers that are in next to our sensor that we can measure the distance to the pipe. And we put the sensor on a 100 millimeter linear slide as well, that we can auto focus the sensor to try to keep it in focus and optimal amplitude and a set distance from the pipe. So we also do scanning. So not only do we use a robot to move the sensor close to the pipe and account for pipe diameter and wobble and everything like that, but we also scan the pipe. And so why is scanning needed? If we didn't scan and we put it in a fixed point location, you're only going to be measuring one pitch of the pipe. So you're going to miss a lot of the pipe coverage. But these coatings are applied with multiple spray heads on the pipe. And as the pipe is rotating in a screw fashion, you kind of get a trail or a pitch around the pipe that it's measuring. So what we'll do is the robot will actually scan back and forth across the pipe as it's moving. So we close in that diameter, that pitch, and we basically measure over all the areas that the different spray guns are covering. So we get try to get 100% coverage of that pipe as it's being scanned. So then what do we do with all this data that we collect? So we basically do a lot of data collection. We collect all the measurements from the sensor, whether it's 1,000 measurements per second or 100 measurements per second. And if there's multiple layers of coatings, we get measurements for all those layers. So if it's a 4-layer pipe at 100 Hertz measurement, we're actually getting 400 measurements per second. And we take all those measurements, we store all those measurements, and then we average those into a display that the operator can then take and use and control their process. So the display here you can see here is a trend that is made as the pipe is being coated, in kind of a machine direction is what we call it. And you can kind of see from the display the colors. It's easy to tell if the pipe is either in spec or out of spec by the colors on the graph. And these are all defined in a recipe that the operators can select by either a product number, batch number, or a pipe number that they preset up. We also can display the data in several different fashions. We can either do it by position of the pipe, so the length of the pipe, or we can do it by time as well. So our displays are very configurable. And all this data is stored in a report as well that operation will pull up after the pipes are created or manufactured, and they can go back and look at the data as well. So the big thing that this system can help do is cost savings. We can help save on raw material usage because we have precision online measurements. You're no longer waiting till after the pipe is made to destructively test. It minimizes overcoating. We minimize undercoating and creating scrap where you will have to come back and recoat. We also offer a closed loop control. So we can send these signals back to the line, and the line can then control the line speed of the pipe or the spray heads to control these coatings. And we just got some, kind of figures here on the bottom showing that, if we can make it a moderate approximation of a 10% savings on a couple different coatings, how much it can save you. And it can easily add up, from, several $100,000 a month, depending on coating prices and the amount of coatings you're using, and the amount of overcoating that you're actually doing. This can also help on avoid having to create sample pipes as well, where they'll create a sample pipe, measure the coating thicknesses, make sure it's right as far as setup. You can actually eliminate the need for these sample pipes, and that can save, quite a bit too, over the life of the line. So the return on investment is pretty quick. So just some conclusions. Terahertz is an excellent solution for measuring multi-layer coatings on pipe. It does a really good job. Robotic development allows for full pipe coverage of the measurement because we're using a robot to adjust for pipe size. We can adjust for wobble, optimal amplitude and resolution of the signal. We've got accurate data displays and full reporting and historian functions to track all the pipes being coated. So operations, process control, and management can go back and look at the history of any pipe. You get a customer complaint, they can go back, pull that pipe number up, and they can see how that pipe was coated. It's safe for operations as well. There's no nuclear, no ionizing radiation. The sensor is fully safe to work around for operations. We also do safety integration of the robot to the line. So we'll do full risk assessments and give recommendations on what kind of safety is needed around the robot as far as interlocking of the cage to the robot. And there's major cost reductions that can be accomplished by using this system. So with all that, I'm just going to kind of open it up to questions. Matt, do you want to take over and kind of let us know
Absolutely.
what kind of questions?
Yeah, thanks, Josh, and thanks, Earl, for that great presentation. I love one of the last bullet points in that conclusion is a cost reduction. I'm sure everyone loves to hear that, so that's wonderful. But yeah, great stuff from both of you guys. Really appreciate it. To the audience, we're now going to move into the question and answer session. You can still send us your questions. You could do that by adding that information to the Q&A box on your screen and click submit. We're going to try to answer everybody's questions today. However, if we don't get to your question for whatever reason, we will reach out after the webinar is over. So please send us your questions or your comments. We would love to hear from you. Okay. Wow, a lot of great questions in the queue here. Okay, let's see what we're going to go with first. Okay. And here it is. First question from our audience. Is the Terahertz gauge certified for this application? I believe this is for Josh.
Yeah, so we're working with some outside sources to basically make this a certified measurement device that can be used with the AMPP Association. They're getting close to getting that done, so that's kind of in the works. So you should be hearing something in the near future with some announcements on that as well.
Excellent. Thank you for that, and thank you for that question. And here is our next question. And what is the current measurement of certifying the pipe coating thickness?
Yeah, so typically these will be done offline, and they're destructive testing. So they're in handheld devices. So they have to wait till the pipes are fully coated, and they'll be using a handheld device that is only measuring, a few spots along the pipe. And that's the major advantage of using this system is you're getting almost 100% full coverage of the pipe, multiple measurements averaged over time, instead of a person using a handheld gauge or destructive testing and just testing a few spots on the pipe itself.
Excellent. Thank you for that. Okay, to the audience, we're in the Q&A session. You can send your questions in by adding them to the Q&A box on your screen and clicking submit. And while you're thinking of your questions, I just want to point out we have some additional information from Quad Plus located in the resource list on the top right corner of your screen. And we do encourage you to access that and take it home with you. Okay, back to our questions. Here's our next question from the audience. How far away can the sensor be? Guys?
So in this application, we typically use a sensor with a 6-inch focal length. So from the end of the sensor to the pipe, it's typically 6 inches. Now we put this inside of an environmental enclosure, and it's also on a linear slide to compensate for focus. So it's a little closer than that, but you're still several inches away. So it's a non-contact sensor.
Excellent. Thank you for that. Okay, moving on to our next question. What is the measurement spot size?
That's an interesting question. We nominally say it's about 2 millimeters. In reality, it varies with the frequency content of the pulse. So sort of a maximum of about 5 millimeters and a minimum of 100 microns, but most of the energy is in about a circle.
Excellent. Thank you for that. Okay, let's see what's next. Wow, we have a lot of great questions in the queue. To the audience, please keep them coming. As mentioned, we're going to try to answer everybody. But if we don't get to your question today, we will reach out after the webinar is over. Okay, and the question is, oh, yes, this actually came in a few different times here, so we will address it. Are there environmental limitations?
Yeah, so terahertz is Environmental factors do not affect terahertz. So temperature, humidity, dust, anything like that. It's kind of environmentally insensitive.
Excellent. Thank you. And that was a great question. Go ahead, Earl.
Yeah, I'll just add to that. This is one of the advantages of making time and not amplitude. If you have dust or even spatter building up on the lens of that issues the terahertz, all it does is delay the pulses that are getting to the pipe slightly in time, but the differential between the top and bottom of the coating remains the same, and so we can always measure it accurately. And the amplitude of the signals that come back are much less important. You know, they figure the signal to noise that we have, but in general, you know, a small change in amplitude is not going to make any difference. So a large amount of dust in the air, or the temperature of the room, or even slightly the distance of the sensor from the pipe makes no difference in the actual measurement that we make.
Oh, that's great. Thank you for that. Okay, let's see what's next. Okay, great. Here's our next question from the audience. What is the coating on the internal wall of the pipe?
Yeah, so with these pipes being a metal, we actually cannot measure on the inside of the pipe. It's because terahertz cannot penetrate metal, so we can only measure coatings on the outside of the pipe.
Yeah, I think that's generally the case. I mean, obviously that the metal pipe, you know, that we're seeing here, it would not be possible to measure the coating on the inside. We have had applications where customers have put, say, a sensor on a long boom that moved into a pipe and looked at the inside of it. But that's, of course, limited in the length. You couldn't do a 40-foot pipe section like these are with that type of a method. But we have gone in, you know, 3 to 8 feet, that kind of range, in order to measure the inside.
Excellent. Thank you, guys. Okay, moving on to our next question. Could it measure delamination in 2 non-ferrous metals layers?
Well, as I just stated, we can't get through a metal. We have measured delamination, but generally in multi-layer plastic or composite products, have 2 metal layers, whether they're ferrous or non-ferrous. They totally reflect the terahertz, and so we would never see the gap between them.
Excellent. Great questions. Okay, to the audience, we're still in the Q&A. We have our experts from Luna, Innovations, and Quad Plus online and ready to answer you, so please send us your questions. Okay, and here's our next question from the audience. Could it be used on a hot pipe, and if so, what's the maximum temperature?
So the sensor itself is rated up to 50 degrees C, but we house the sensor inside of an environmental enclosure. So we can measure hot pipes. The temperature can actually be pretty high as well. And depending on that temperature, we can cool the sensor enclosure as well. And that can be done either with just using plant air and vortex coolers. And we do that closed loop, so we have temperature feedback inside of the enclosures. Or if the temperature is high enough, it could also warrant that we use water cooling as well. So we can handle very, very high temperatures.
Oh, that's great.
Right. The sensor, as we mentioned, can go up to 50 C. So as long as we stay below that, we're good. We're going to get a valid measurement. What Josh, in this very application that we're looking at, the pipe is heated up to about 200 or 300 C, and then they spray on a powder coat that then fuses on contact. So these are looking at very hot pipes in the examples that he's showing here.
Excellent. Thanks, guys, for that. Okay, let's see what's next. Okay, great. Here's our next question. Can we know the error tolerance?
Earl, I think you kind of touched over that, but can you go back over that maybe?
Yeah, sure. I did show a slide on that. I think I can bring that up. Yeah. So this was a long-term measurement. This is not probably a better one would be the slide before it, where I was measuring at a kilohertz. I'm measuring this 3 millimeter thick object, and I'm doing it to less than a micron. Now this is of course a very ideal case. I think you're generally going to see, and it depends a little bit on exactly what the customer and how you've set the measurement up. If you need full speed, in other words, single waveform to make each measurement, then that's going to limit you some. If you have materials that are maybe absorbing in some way, you may get a little less resolution or a little less precision because of the absorption in the material. If you if you're in or out of focus, it can also have some effect on it. But generally, we found that examples like this, if you're going to, and I don't know if our audience thinks in metric or in English, we've gone to a fraction of a mil, obviously, for in thousandths of an inch, or in a few microns is a typical online kind of tolerance or accuracy, if you will.
Excellent, great, thanks, guys. To the audience, we're somewhat nearing the end here. We're getting down to it. So if you have any last questions, any last comments, now would be a good time to send them in. We do have some more questions in the queue we're going to get to in a moment here. But as mentioned, if we don't get to your question, we will reach out after the webinar is over. Okay, and here's our next question. How can we verify the calibration of the system?
So typically what we would do here is the customer can provide a standard sample. The standard sample will be mounted in a known location that the robot knows about. It's actually a sample holder. And operations at any point in time can move the robot to that sample position and verify the thickness of that standard sample. There's also ways that we can do continuous online verification of the system as well. Earl, can you talk about that a little bit? About adding possibly like a fused quartz sample into the system for continuous testing?
Sure. And maybe the best thing is to go back here. We have sensors, the typical sensor is the one here in the middle called standard terahertz industrial collinear sensor, where we're just, the pulse is coming out and we're reflecting off the one to its right actually uses the second beam, just like the lower one, to reflect with that little sidecar device on the side, reflects the beam up to either a metal reflection to just give us an amplitude measurement or a timing standard within the sensor itself, or we can replace that with a quartz plate. And in that way, we can get the reflections from both sides of that quartz plate and continue to the terahertz thickness that we're getting. I should add, though, that there's two parts to the question. One is, how do we know that the time I'm measuring is really the proper time? Okay, and that has to do with the calibration of the terahertz control unit. And that, because of the method of that calibration and the way that it's actually a physical mechanical distance, that's very stable over time, and we typically do not see any drift in that calibration, although we can, as I said, confirm that with this internal quartz plate. The other kind of calibration is when you say, okay, I know how thick, I know what the time delay is between my two reflections, but what's the speed of light that's in between there? That can vary with material that's being used. And so that's more what Josh was talking about in comparing it maybe to laboratory measurements from the plant where you can then just adjust the calibration that you're using so that you get the precise thickness. We have also, in certain circumstances, been able to implement that online as well, using two sensors or a sensor and a reflection plate. We can sometimes do an calibration of that on the fly. So there's a lot of opportunities with a terahertz sensor that we didn't get into today, but those are the typical ways that we make sure that the calibration is correct.
Oh, that's great. Thank you for that, guys. To the audience, that may have been our last question, but we're just going to wait a moment here. If anyone else has another question or comment, please send it in right now, and we will try to get to it. Again, as you're thinking of that, I just want to again mention on your screen, we have some additional resources from Quad Plus. You can access that in the resource list on the top right of your screen. Okay, and it looks like we do have one other question that came in here. We're going to address it now. And so here it is. Which polymers, besides PP and PE, can be coated on steel pipes by Terahertz process? Guys?
Josh, you've looked at multiple coating types, right? You had a couple of slides on those.
Yeah, let me go back to a previous slide here. So it's really, I mean, any coating that can be applied, as long as there's a refractive index between the coating that's next to it, it can be measured. So whether it's a FBE adhesive or PPE, let me go to the next slide here, or AROs or FBEs. Any of these coatings can really be measured as long as the refractive index is different than the coating above it. That's the main thing, differentiator between it, whether you can measure two coatings or multiple coatings, is the refractive index between those two coatings.
Right, and I'll add to that. We have looked at certainly at paints, typical paints, with primers and overcoats. We've looked at various highly absorbing coatings, some that are used by the Defense Department. We've looked at many different types on materials. As long as they're not conductive, we can typically see through them. And we've done, in fact, one of the other ones that's more current is we're looking at cathode and anode coatings in batteries, for example. Again, that's a coating on a metal substrate, and very typical, similar to this application, but a completely different use case.
Oh, that's great stuff. Thank you both. Okay, and it looks like that indeed was our last question for today's session. So we are going to move to wrap things up. So once again, Earl and Josh, thank you so much for the great presentation, and thank you for taking the time to answer some questions from our audience today. And of course, we'd like to thank our audience members for being part of this webinar event. You will be receiving an email from us with a link to the on-demand version of this presentation, so you can come back and watch this again or share it with your colleagues. And lastly, please take a moment to complete a survey which will appear on your screen at the end of this live webinar. For on-demand viewers, you will find the survey located along the bottom of your attendee console in the survey widget. Again, thank you for taking the time to attend this webinar event. Take care, and we will talk with you soon.